All right, so I have an ideal diesel cycle. I'm given the initial pressure, temperature, volume. I've got the compression ratio and the cutoff ratio of defined what each one of those processes are, so I can be specific about what I mean by state one. And then of course I need the unknown pressures, the unknown temperatures, the thermal efficiency, the work net out, and the mean effective pressure. I'm making air standard assumptions. I'm assuming kinetic and potential energy changes are negligible, and that makes the my first law of thermodynamics a little bit more simple. I get things just in terms of delta U, Q in, Q out, work in, work out. All right, so first thing I need to do is get my governing equations. So I'm going to get those. So my thermal efficiency, it's big W net out over Q in. That's how it's written on the equation sheet. And of course, I could put things in terms of little w's and little q's. And then I remember for any cycle whatsoever, power cycle, refrigeration cycle, doesn't matter, any cycle whatsoever, the work net in is equal to the Q net in. And so this is any Q in minus Q out. And so my thermal efficiency can be written in terms of 1 minus Q out over Q in. And if you need a little refresher on how to define that Q in and Q out, I recommend that you go back to that video that introduces the diesel cycle, because we walk through each one of those processes and apply the first law and get our equations for Q in and Q out and work in. All right, so my big W net out, make sure I multiply that little w by the mass. I can define the mass using the ideal gas law. I can define that work net out as Q net in, and I've got my Q net in defined up in the thermal efficiency equation, so I'm good to go there. And then I get my mean effective pressure, so it's written in terms of big W and the displacement volume. And I can divide through by mass and get things in terms of little w and specific volumes. So maximum is before compression, minimum is after compression. Then I could rearrange that specific volume. I can define the V2 based on V1. So you can look at these two. You can look at those last two equations on the denominator. So V1 times 1 minus 1 over R. Well, 1 over R would be V2 over V1. So you can see if I multiply by V1, it would give me my V2. So both of those are the same, just different ways of writing it. And that specific volume I can define in terms of the ideal gas law. So I'm ready to start plugging in numbers. At state one, I see the only unknown that I have. I need the U value to figure out parts C, D, and E. So U, I'm just reading it off the table at T1, which is given to me. And I'm going to table A22, my English unit tables. State 2, I need temperature, enthalpy, and pressure. So I can apply an isentropic relationship between states 1 and 2 since it's an isentropic process. I do need VR1, so I pull that off of the table, plug it in, and I get my VR2. And the reason that helps me is because I can go to my ideal air tables, and at VR2, I'm going to have to do some interpolation, but at VR2, I can get my temperature and I can get my enthalpy. And then I could go and get my pressure. So I could apply an isentropic relationship, but that's gonna, so the P2 over P1 equals PR2 over PR1. I could do that, but that's gonna require me to do a little bit of interpolation. I don't really wanna do that. So I'm gonna apply my ideal gas law. Of course, my specific gas constants, those cancel out. I know the relationship between V1 and V2. That's just my compression ratio, and so I can solve for P2. Now I moved on to state 3. So I need temperature, enthalpy, and pressure again. I cannot apply an isentropic relationship between 2 and 3 because it's not an isentropic process. However, my ideal gas law is always applicable. I note that P2 and P3, because it's a diesel cycle, are equal to one another. So I've got my pressure there. And then my ideal gas law simplifies and I can calculate my temperature. And then my enthalpy, I could just read off at that calculated T3 value in my tables, table A22E. Now I go to state 4. So I need T4, U4, and P4. Well, I can apply an isentropic relationship between 3 and 4. And then I can, I don't really know V4 over V3, but I can rewrite that. So you can see, let's see what we've done here. So V1 is equal to V4, right? So I haven't really changed anything. The V2s are going to cancel out. And so now I've written things in terms of the cutoff ratio and the compression ratio. And then I do need VR3. So if I plug that in, I get my VR4 and I can read off T4 and I can read off U4. And then, of course, I need to figure out what P4 is. I'm going to use my ideal gas law. So I could have done it I could apply that ideal gas law between 1 and 4, or 3 and 4, or really 2 and 4, because each of those quantities on either side of the equal sign, if we're saying it's an ideal gas, we're saying that each of those quantities is equal to 1. And so, well, if I had a mass there, but that's can't. No, that's okay. That's the way it is. So we're saying each of those quantities is equal to 1. And so it doesn't really matter, what numbers are on either side. But the reason I chose that is because between 1 and 4, that specific volume is constant, so it just cancels out. And so now I've got my P4. And if I plug everything in and just be sure to, actually go through the practice, make sure that you see how your units cancel out, do any unit conversions that are necessary. But these are the numbers that you should get for the thermal efficiency and the work net out and the mean effective pressure. All right, well, I hope that was helpful. Thank you for watching, and let me know if you have questions.